This video will show the basic usage of Delphi software and an example showing how to calculate the Born radius of an atom. Delphi is a software that can calculate the electrostatic potential and electrostatic solvation energy of biomolecules by solving the Poisson-Boltzmann equation. The software can be downloaded from our group website, compbio.clemson.edu/Delphi. Now let's get familiar with the basic functions of Delphi with an example. In this example, we are going to calculate the Born radius of a single atom. All the example files are also available on our group website. By clicking the Delphi example button, you can download all the examples in a zip file. So after you download all the files and unzip the files into a folder, you will find 8 examples. After we get into example 1 single atom folder, we will see 4 files. The Born.chart CRG file, and Born.pdb is a PDB file, and Born.siz is a size file. Finally, there is a parameter file. And let's have a look at the parameter file first. More parameter. So we can see a lot of parameters in the parameter file. The first one is G size equals 95. G size means grid size. Here we have 95 grids on each dimension. And scale equals to 2.0 means we have 2 grids per angstrom. Usually we use scale equals to 2.0 as a commonly used parameter for scale. Sometimes we can also use 1.0 for a lower resolution and 4 or higher for high resolution. Following by the 3 input files, PDB file, the size file, and the chart file. The INDI equals to 2.0 means the internal dielectric constant equals to 2.0. This one is for the protein or the atom we are interested in. The external dielectric constant is set to 80 for water. Sometimes we can also use 78 or some other numbers for the external dielectric constant. The output file is a PhiMap file. It's phi, and file name is PhiMap. The format is cube. Cube means a Gaussian cube file. The prop radius to build the molecular surface is set to 1.4, and the salt concentration is 0.1. And the boundary condition is 2. Type 2 means dipole boundary condition in this case. And we said the max change in iteration is 10 to the minus 4, which means when the change in between consecutive iteration is smaller than 10 to the minus 4, we stop the iteration. Or we stop the iteration when we reach the linear iteration limit equals to 800. Finally, we will calculate the energies. We will calculate the solvation energy S, Coulombic energy C, and grid energy G in this case. We will have the 3 other input files, the charge, PDB, and size file. So in the charge file, we have the charge of the atom we are interested in. Here we have a nitrogen atom in a valine residue. We set the charge of the nitrogen atom equals to 10. Usually nitrogen will not have a charge of 10, but in this case we set it to 10 for an easier example. The PDB file is in the normal PDB file format, as we downloaded from the pdb.org. So here we have the atom, nitrogen, in valine, and its coordinate is 0, 0, and 0. In the size file, we have the size of the nitrogen atom. We set the radius of the nitrogen atom to 3.0 angstroms. So after we look at all the files, we can go ahead and run the Delphi executable file. So we type the name of the Delphi executable file and then followed by the parameter file and type enter. The simulation only takes about 1 second to finish. So in this simulation, we have 210 iterations, and at the end of the iteration, we reach a maximum change of 1.5 times 10 to the minus 5. So it's smaller than 10 to minus 4. So we only evaluate the max change every 10 iterations, even though the max change could be smaller than 10 to the minus 4 at 205 iteration steps, but we still need to run the iteration for 210 steps. And we calculate the following energies: the grid, Coulombic, and some other energies here. So we have a warning at the end of the simulation. It says Waiting 10 has a net charge of 10. So because we set the charge of nitrogen to 10, so the net charge of the Whaling is 10. Usually we have amino acids with 0 or close to 0 net charge. When we detect some amino acids have abnormal charge, we will pop a warning to remind you have a look at the input files. So after the iteration, we have one more file. Is called FileMap.txt, and then we can use VMD to visualize our results. So we open the VMD, and load the structure file, the PDB file, into VMD. We set the drawing method to van der Waals radius. So here we can see the atom here. And then we load the file map data into PDB file, into the structure. We select format to Gaussian cube, click load. Right? Then we have some data here, but we cannot see the file map. We need to create another layer to show the file map. We select the drawing method to ISO surface. And if we zoom out a little bit, we will see the box. So the box here represents the grid we set earlier in our parameter file. It's 95 grids and 2 grids per angstrom. We select the draw method to solid surface. And the ISO value, let's set it to 4. So the number ISO value here means the electrostatic potential in the calculation. The unit of it is kT per E. So here we are looking at all the points with electrostatic potential equals to 4 kT per E. And we set the material to transparent and change display method to So here we can see the atom is in blue and the electrostatic potential surface is in white. Alright, so now we are coming to the end of the first example for Delphi program. In the next example, we are going to show you how to calculate the electrostatic potential and surface for a real protein. If you have any question about our software, please go to our website and click Contact Us to send us messages. Thank you for watching, and see you in our next example.